Hey everyone, welcome back. And so today we're going to look at divider circuit and circuits and divider circuit methods. So the first one we're going to look at is a voltage divider method. And essentially this just means that it's a series circuit. So all series circuits are voltage dividers. And so in our example here, we have a series of three resistors, R1, R2, and R3. And we have this input voltage that's across the two terminals of this circuit network. And so what this is going to do is divide this voltage across these three resistors. And this comes from Kirchhoff's voltage rule or voltage law, and that this voltage rise must be equal to these three voltage drops. So these add up to that. And that's what we're working with here. So we're going to start with looking at V out. So V out is essentially V3, the voltage drop across resistor 3. And so we write that as our element equation. So V out, using Ohm's law, is going to be related to the current through resistor 3 and the resistance of resistor 3 itself. So V3 is I3, R3. We're looking at V out. So V out is also I3 times R3. The other important equation here, we're already using Kirchhoff's voltage loop law, and we're now going to look at Kirchhoff's current law. So in series, the current through each of these resistors is the same, and indeed it's equal to the current coming into the whole two-terminal network. And so IN is equal to I1 is equal to I2 is equal to I3. And I3 is something that we're interested in, and we're going to relate I3 back to our input current right there. So here, those are boxed to show that. So one thing we have to do is figure out the equivalent resistance here. And if we do, we find the equivalent resistance for a series circuit is just the sum of the three resistors. So that's R1 plus R2 plus R3. That's the equivalent resistance. And so that's equal to the input resistance. So if we were to make that equivalent resistor, then we see we have an input current, an input voltage, and the resistance here. So since there's only one resistance, this is the input resistance, and it's also, we found it by finding the equivalent resistance of these three resistors. And so now going back to an element equation for this equivalent circuit, we see that the current IN is equal to VN over RN. And so that's going to allow us to develop our voltage divider rule. And so now I'm just going to substitute. So Rn, we can substitute from here. The equivalent resistance is R1 plus R2 plus R3. And so we have In is Vn over R1 plus R2 plus R3. And we're looking for V out. So I'm going to go back and look at our equation for V out from the element equations. And that's I3 times R3. So copy that down here, I3 times R3. Then substitute for I3, we see In is I3 by the current law. And so we substitute In for I3 because we want this in terms of In and Vn if we can. And then we have In right here. We have voltage in over R1 plus R2 plus R3. So substituting that, we come up with that V out is Vn times R3 over the equivalent resistance of that two-terminal series network, R1 plus R2 plus R3. And so we can write that V out is Vn times R3 over R1 plus R2 plus R3. So essentially what we've done here is picked the resistor that we were interested in to look at the voltage across, that was R3, and then divided by the equivalent resistance of the whole network, which is just the sum of the three resistances. And that factor then is multiplied by our input resistance, and then the result of that is the output across R3, or the input voltage, and the result of that is the output voltage across R3. So again, the output voltage is just the input voltage multiplied by this factor, which is the resistance that we're interested in over the sum of the resistances in that series circuit. So in general, then we can write that for any strict series of elements, so this is just series and no other connections leading out from here, just a series network, then we can say that the X voltage across the X resistor is going to be equal to the V out, that's what we're interested in, and that's going to be our input voltage across the whole network times the resistance of the resistor we're interested, our X over the whole input resistance, which is again just the equivalent resistance, which is the sum of all those resistors. So here is the expanded form of that. The X voltage is going to be the input voltage times the X resistance over the sum of however many elements you have. And so this is only 3. We could have as many as we want, and we can pick any of those resistors and quickly find, using this voltage divider equation, quickly find the voltage across that element. So it's pretty cool. Current divider works in a similar way. Let me just make sure that we're all in frame here. Perfect. Okay. So current divider works a similar way, except that when we talk about current divider, we're not interested as much in the resistances because we're in a parallel circuit. We're interested in the conductances. So first off, parallel circuits are current dividers. This comes from Kirchhoff's current rule that says that any current into a node, and here we have the node on top, is equal to the current out, but we have 3 currents coming out, I1, I2, and I3. So I1 in is divided into I in is divided into I1, I2, and I3, and so hence it's a current divider. And so since conductances add in parallel and resistances don't, and there's a more complex formula for that, we're going to look at the conductances here. So again, we have our source voltage, input current to our 2-terminal parallel network. So the element equation that I may be interested in is the element for I3. So this is the path we're looking to find the current in. And it's Ohm's law again, but it's the conductance form. So I3 is equal to G3 times V3. The circuit equation, we already used the current law, so this is the voltage law. So any voltage gain around a loop is equal to the voltage drop, and we can see that each of these includes a singular loop with a singular resistor and the input voltage. So Vn is equal to V1, equal to V2, and equal to V3. Since we're interested in element 3, I've boxed that V3 and Vn are equal to each other. So we're going to find again an equivalent circuit. In this case, we're looking at the conductances. And so in parallel, the conductances add. So Gin here, or Geq, is going to be equal to the sum of the 3 conductances. And then we have something similar that we did for the voltage divider rule, except now we're looking at conductances here. So I can write the equation for this simplified equivalent circuit in terms of the conductance Ohm's law. The input current is equal to the input resistance multiplied by the input voltage. Since we're going to want to substitute in for Vn so that we end up with In, I'm going to rearrange this so that voltage in is equal to In over Gn. And I get this, that the voltage in to our network is the current in divided by the sum of the conductances. So this looks really similar to the last one, except that In and Vn were switched, and these were the sum of the resistances for the voltage divider equation. So then I'm looking for I3. So I can start with the element equation for I3 and just substitute in from there. I3 is G3 times V3, but we also already know that V3 is equal to Vn, so we can substitute for Vn, G3 times Vn. And then we found an equation for Vn as In over the sum of the conductances. And so substituting that, we get In over In multiplied by G3 over G1 plus G2 plus G3. And so the output current, or the current through element 3, is the input current multiplied by the conductance of element 3 divided by the sum of the conductances in the complete parallel network. And so then rewriting this here in a nice form, I3 is In G3 over the sum of the 3 conductances. This is specific to this 3 resistor network as we defined it, but we want to use this in a more general sense for any number of parallel resistors. And so in general, for any parallel set of elements, we can simplify this to the X current for the X element is equal to the input current into the whole network multiplied by the conductance of the X element divided by the whole input conductance. And so expanding that out, that's just the sum of all the individual conductances. So again, if we're not looking for everything in the circuit and we just want to find the current through one path, this is going to simplify the amount of work that we have to do to actually find that value. So let's do an example where I'm not going to do a simple example because you can just get that right from the equation, but let's do something that we can use this when it's even a little bit more complicated of a circuit. And so what we have here is we have a source of 10 volts, And then we have two resistors that are in series with the source, R1 and R3. I made a mistake here, and I just started to go to 3, skipped 2. And then we have a parallel element here where we have R4 in parallel with R5 before we return to the bottom node beneath the source. And these have 4 and 5 ohms respectively. So what if I wanted to find the current through the path of R5? And so what is the I5 current? And so at first glance, if we were to do this with the equivalent circuit method, we'd find the parallel and we'd add it all up, and then we'd find the series current, and then we'd have to divide out this parallel again and then figure out what current was going through R5. So we can do this a little faster using the current divider method, and I'll show you how. So we're trying to find I5. We can only use the current divider on a strict parallel circuit, so the only place I can use it is right here. I can't use it including these two series resistors. So really I want to get this down to where I know the current entering that parallel section, and that's what we need to find. And then once we do, then this is a strict parallel circuit. We have the input current, and then we can use current divider to find out what the current is through R5. And at that point, I5 would just be the input current multiplied by the conductance of 5 over the sum of the conductances of R4 and R5. So first thing we need to do is find this I in. So we can use the equivalent resistance method to do this. So I find an equivalent resistance for the parallel combination, and by our shortcut, it's the product over the sum of R4 and R5. So we get 4 times 5 over 9, so that's 20 over 9, or about 2.22 ohms. And so then, knowing that that's 2.22 ohms, I can add that in series with 2 and 3 to get our equivalent resistance for the whole circuit, and that would be 7.22 ohms. And we have our source current, and using our source current now, I know that looks like I5, it's supposed to be IS, and that's VS. So our source current and our source voltage divided by our total equivalent resistance gives us a current entering into the circuit of 1.38 amps. So 1.38 amps is entering into the circuit. Now let's look back over here. So 1.38 amps by Kirchhoff's current law, it's going to be the same 1.3 amps here. By Kirchhoff's current law, it's going to be the same 1.3 amps here. So entering in to our parallel network right here is 1.38 amps. And so right here we just found I in is 1.38 amps. So I have 1.38 amps now coming into our parallel section, and at this point I can just apply the current divider rule. And so I5, this is now I5, is I in, that's at 1.38 amps, divided by, or times the conductance of 5 divided by the sum of these two conductances. So let's find the conductance of 4, so it's 1 over R4, and that's 1 over 4, it's 0.25 Siemens, and then G5 is 1 over R5, it's 1 over 5, gives me 0.2 Siemens. And so then just plug these into the equation. Input current 1.38, 0.2 for G5, 0.25 for G4, 0.2 for G5, add those up, multiply them together and divide, and we get 0.613 amps. And so that's less work than we might have to do if we did it in just the equivalent circuit method. So let me show you that we can also use voltage divider for the same exact circuit, and it will again reduce some of the work that we need to do. So here's the same circuit, but I've redrawn it in a little bit of a different way. So this is what we would call an equivalent schematic. So it's the exact same circuit, but we just drew it differently. And so we have two series resistors, R1 and R2. This time I labeled them properly. And then a parallel section, R3 and R4. So one thing that you can realize here, that this is 3 elements in series. This element R1, this element R2, and then this kind of combined element of R3 and R4 in parallel. So if I can get this into just being one resistor, an equivalent resistor, then I can apply the voltage divider rule and then go from there. So we recognize that they're in series, so we need to find REQ1, which is the parallel combination of R3 and R4. So we do that just like we had in the last one. We find it as 2.22 ohms. So this is our circuit now, 2 ohms, 3 ohms, and 2.2 ohms for this equivalent resistance here that will expand back out to our parallel circuit. So now I use voltage divider here. So the voltage across REQ1 is going to be the voltage into the 2 terminal series network. And so we have 10 volts. And then we use the equivalent resistance divided by the sum of these 3 resistances. and we just plug in. So 10 volts times 2.22 divided by 2 plus 3 plus 2.22. And if I solve that, I get 3.08 volts. So there's 3.08 volts across the equivalent resistance here. So now let's expand that back out to the parallel circuit. So we have 3.08 volts. When we expand it out, you can see that there's still only 2 nodes, and that's by parallel rules. The voltage law says that in parallel, the voltage drops across all the parallel elements are going to be the same. So when you expand this equivalent resistance into a parallel circuit, we still have the same voltage. So there's 3.08 across this one and 3.08 across this one. Well, we're looking for the 5 ohm resistor's current. I have 3.08 volts across it, it's 5 ohms, and now I can use the circuit equation, the element equation for R4 that says that I4 is V4 over R4, so that's 3.08 divided by 5, and I get 0.615 amps. So pretty quickly we get to the current through this 4th resistor, this 5 ohm resistor. And you notice on the other page we got 0.613. There's a little bit of rounding error here, but it's the same answer if we include rounding errors. Okay, thanks for watching. That's all I have for you guys today. Have fun with your homework.